All right, here's our man-made resonator, which has it's a double barrier structure with length L. And on the right, I'm showing you a parabolic dispersion, an EK diagram. So we know that there's a ground state that is confined in this particle in the box as pi over L. Right? We know we're going to fit a half wave in there, ballpark, and we can argue how long that L is. But let's just say it's at K0 at pi over L. So we can go in our dispersion here on the right, find that K0, and we can map it into the device. That is in fact what was being shown in the PCPBT tool a few lectures back. Right? We have shown that a particle in the box problem is related to this resonant tunneling problem, and you can roughly relate the resonance energies like that. The details are more complicated because these barriers have energy-dependent coupling constants. So it's not quite clean, but for analytical purposes, let's just show this is how it works. All right, now your excited state should have two lobes in it, right? So it's 2K0. It should be 2 pi over L. So let's double that K in that dispersion, and we can read off that excited state. Another way, again, to look at that is we have a dispersion in the forward, say the Z direction. We know that K no longer is a good quantum number. It is quantized due to the discretization of our heterostructure. And we, instead of having a continuous dispersion E of K, we have picked out K points that are discrete now. That's another way of looking at this. All right, so what's the big deal? Well, the big deal is that indium gallium arsenide in particular is not very parabolic. It's very non-parabolic. All right, so you draw this dispersion in that's a little bit more realistic, and you say, okay, well, it doesn't look too different. Right, it's still parabolic. And you can say, okay, my ground state, in fact, is roughly at the same energy. So nothing much happened, right? So no big deal. Well, forget about all this complicated stuff with band structure. Well, let's look at the excited state. The excited state can be much lower. Okay? In fact, it can be lower by, say, 100 millielectron volt. 100 millielectron volt at room temperature is 4 kT. That is 4 orders of magnitude more occupation on an exponential scale of a Fermi factor. There's suddenly 4 orders of magnitude more carriers available to be transmitted here versus being transmitted up there. That's going to be a little bit of a difference. All right. So the result is that it's really important for the second turn-on of the IV. So what I'm showing you here is one of the test devices at room temperature. In blue and green are the experimental data. And in light blue is a single band calculation. And in red is a full band, full transverse K calculation with full band. And you can basically see on a linear scale, it seems like the single band calculation never turned on. So let's look at a log scale and see how bad it is. On a log scale, you're off by 2 orders of magnitude. Your valley current is wrong by 2 orders of magnitude. Meanwhile, a full band calculation that understands this non-parabolicity is pretty much dead on. Close to dead on. Okay, so there's something fundamentally missing if you just do effective mass that doesn't include non-parabolicity. But there's something more. The single band is missing the peak. But we had argued that the peak is roughly at the same energy, right? Nothing happened apparently there. So we're missing some other physics that I haven't quite explained to you yet. But there's something missing in the single band calculation that is present in the full band calculation. So let's look at that. So for argument's sake, let's look at a single barrier. Let's say we have indium gallium arsenide and indium aluminum arsenide barriers, and we're wanting to inject a carrier into an electron into the device. It's going to penetrate roughly into the middle of the gap of this indium aluminum gallium arsenide. Indium aluminum arsenide, sorry. And we now know sort of from our analytical expressions from the previous lectures that, well, there's a decay constant of that propagating wave of e to the minus kappa L. It's an exponential decay. So, and how would we get that kappa? Well, we would draw a an EK diagram for the barrier material up in real space, right? Here's a real K. And if we just know about one band, we've just written always that there is a parabolic dispersion in the complex plane. So we would grab a kappa out of this complex plane. So if we inject, say, roughly at this energy, we would read off a kappa that has some value. And that would give us the attenuation constant of our wave into the barrier. Okay? But the fact is that these bands are coupled. That there is a valence band that sits at a lower energy that might look like this, and these bands talk to each other. And they're coupled in the complex plane. That means if you're now injecting a carrier at this energy, the proper kappa is actually a much smaller value. Because you're really only matching this complex dispersion right at the top of the barrier. They might have the same slope up at k equal to 0 or kappa equal to 0, but then they wrap around and the parabola keeps going, and the wraparound part you don't catch. Okay? So now you compute a kappa that is much smaller, and the kappa goes into the exponential. So kappa is smaller. What does that mean? The attenuation is smaller, or the barrier is much more transparent than you think it is. Okay? Well, if the barrier is much more transparent than you think it is, your resonance is going to be much broader, and therefore the current is going to be much higher. Okay? That's the key element that brings you from a peak current that's too small to too high, to just right. That's the other physical intuition that you need to understand why this is the right physical result. On the log scale, again, you see that basically the single band curve gets raised up by ballpark an order of magnitude. Okay? And you can somewhat mimic that by faking the effective mass in the barrier. You could make the effective mass in the barrier lighter and therefore make the dispersion go sharper in energy and decrease that kappa. Well, yeah, you can make any curve fit to whatever you want, right? If you just pick a parameter out and then make it different for another barrier and make it different for another barrier. The point is, if you want to do device engineering, you don't futz with material properties, right? You have a material database, you pull in the database, you trust it, you don't mess with it, and you put in geometry data and simulate. You don't mess with your basis functions on the go.